So does my mic work on this stream? Let's test it out. Okay, sounds like it's working. Oh, we got another viewer. That's crazy. If you're watching the stream, oh, he's gone. Yo, who's in the stream? Please leave a comment or just like let me know if you're watching this. I want to make sure that humans are watching the stream and not bots. Okay, so we have this Mars thing. You need powerful thrusters to get there. Let's draw another diagram. You're not a bot. Okay, awesome. That's really good to hear. Yeah, so what am I doing? I'm planning out how to get to Mars and make it habitable and stay on there. That's what I'm planning right now. No resources except for like a Wikipedia article right now. So you start with Earth here. I don't even know how to spell Earth. Okay. So this is Earth. Has some like water, chunks of land. And so we want to get to Mars. So what do you need down here? You need rockets. Right? So some points here are like you need thrusters, you need replicates of both fuel, because you want reusable rockets. And this should be something you can create on Mars. What else do you need? You probably want AI to be helping you because it's going to be hard. Taking care of Earth could be a better option. It already has everything. Yeah. So taking care of Earth is really good. However, there's a decently small risk that every century or every decade, we bomb ourselves to death with nuclear warfare. So, would you rather have every single human you've ever known, times 8 billion on here, and just always like pretty much everyone would be wiped, right? If we had a nuclear warfare, we'd pretty much all be wiped, or at least most of us. And given the chance that we might all die, it's good to have a plan B, right? So if you have maybe 1,000,000 humans or 1,000 humans here, they'll surely be able to understand that Mars or that Earth was like bombed, right? Speed of light will essentially allow us to communicate between Earth and Mars, and we'll figure that out. So it's kind of just a plan B. Call this. Let me get a new marker. This is called Plan B. And the thing with current, like I do not disagree that staying on Earth is okay. I think we should totally conserve this planet and use it as much as we can and try to like keep it alive and everything. But we can't assume that that's going to hold true forever. So you need plan B. You need to go explore other planets. So while taking care of Earth could be a better option. Yeah, I think you don't need to focus on one either, right? So there's like there are many sub-problems that you tackle when you bring up the idea of space exploration versus staying on Earth and taking care of it. So one, there are 8 billion people on this planet, and so we can sustain it for quite a while. Meaning we can do a bunch of things at once. I don't know. I don't know what much I don't know much more to add than that really. Like you have a bunch of people that can be working on either sustaining Earth or making life multiplanetary. You don't have to pick and choose really. So you can do both. It's like, you know, you can have accountants and software developers in the same company. You don't need just one. So step one. Step one is A. So you send it over to Mars. Set up, and it sets a bunch of bases up, right? So you get these robots or artificial intelligences to essentially set up base for you. So set up base. Number two, you use this to terraform Mars. So terraforming means you use nuclear bombs. I actually added this. Yeah. Yeah, I put terraforming here. Bombs. So you use bombs. I feel like I'm talking to myself. You essentially just vaporize the surface of the Earth. You vaporize it, and then below there's a bunch of ice that also gets melted. And you can use that ice, and it's like water, and you might find life in there. But the life probably isn't good enough to help us. So you could just study it, and that's about it. However, just put bombs. Okay. Yeah, I'm just sorry about that. I'm live streaming. So it's on YouTube as well. I'm doing this and YouTube thing so I can like attract a bunch of people. But yeah, right now we're just going through the whole space exploration thing, colonizing Mars. Um like from scratch from what we have today. So you can choose to agree with me or not, but first of all, you have to sort out, is Mars actually worth going to, right? So is Mars worth going to? And I sort of proved why it's worth going to down here. So I pretty much said you have this plan B, right? If we bomb ourselves or if something happens on Earth that wipes out like almost 100% of humans, then, you know, if everyone's on Earth, then it's like you've kind of just lost. Or you have to rebuild, which will take hundreds of years, perhaps even thousands. And so I propose plan B. You go to a different planet and set up infrastructure there using uh, at most 1% of the world's economy, which is almost nothing. So 1% of the world's economy is like I don't know, maybe like a few $100 billion, maybe like $1 trillion per year at most. It's not that much. I mean, it is a lot. It's a lot for space exploration, but it's not that much in the grand scheme of the world, so we can afford it. And you might ask, well, you can either choose to help preserve Earth down here, or you can focus on Plan B up here. And the answer is no, that's wrong. You can do both. Humans can do both. I gave an example earlier where if you have like a company that does accounting software, to do the accounting software, you're going to need both software developers and accountants. So you don't just need developers for it. You need both, right? You need both to survive. You need to sustain life on Earth through like environmental practices, electric vehicles, solar panels, energy, etc. And you also need to be focusing on Plan B, because what if something happens here? Then nothing of that matters. Nothing matters on Earth. And if you only focus on here, well then, what if we want to go back to Earth or something, or if there's something there that we need? Well, we can't really access that directly, can we? So the point is, focus on both. And the first step you're going to need to colonize Mars, assuming we've like decided, okay, Mars is a good idea, is use AI to set up infrastructure on Mars. So like bases, right? You have the surface of the planet, and you set up a bunch of bases, right? One here. You put like a Mars rover, and it looks around and does some stuff for you. And this should be done entirely with AI. It is not very safe for humans to go to Mars and expect a trip back. So you can't really do that. Well, you can, but you know humans need to be prepared to die in that case because it's pretty hard to do. So you get AI to do this for you, and the AIs will stay on the planet, and they'll get their energy from solar, or maybe they'll even set up a nuclear reactor, and you can do more with that. But that's a whole different story. The point is, set up some infrastructure so that humans can actually go, where you can do more experiments. And before you get humans to go on Mars, terraform with bombs, right? So you've ever seen a nuclear bomb before, like in the movie Oppenheimer? This massive, like, this white light, it just vaporizes everything around it, and that is what you're going to use to terraform this. So on Mars, there's... Yeah, exactly. So you nuke the poles because those are the coldest, and you have a bunch of these layers, right? These are Mars's like layers. So you got like crust, you know, a little bit below the crust, mantle, etc. You just melt a little bit of the crust so that you can get this potential water and life. There's potential life down there. It's likely frozen because all this water that we've found is frozen, but you vaporize the surface and you get all this extra water. And this is great because humans need water to live, and we can use water for a lot of things, so that's good. So you terraform, you heat it up a little bit because Mars is ridiculously cold, and you use that heat from the hydrogen bomb, which is not radioactive. It would be, if it is powered by fusion, it will not be radioactive. It will, I don't know, you might have some plutonium from like activations, but that's a whole different thing I'll go into later, nuclear fusion. So the point is you build a bomb that's not radioactive, you heat up the surface, humans can live there because now it's like room temperature, right? Everything around you is like 50 degrees hotter, so like you're going to have lower temperatures of like minus 30, minus 20 Celsius, and then higher temperatures of like, you know, plus 40 maybe. So it's going to be like Earth temperature, and that's good. So terraforming is a good option because there's no life or anything that we could like destroy there. Nothing that's really, no damage that could really be done other than getting us humans on the planet. And then number 3 is setting up your rockets. So we're going to assume that during these stages, your rockets are already set, right? You probably built some Starship rockets. Elon Musk is working on that now. Number 3. Rockets So this is pretty self-explanatory. You get rockets, and you get humans on the planet. Now humans can start doing things. It's warm enough for them to function, and you have a bunch of these super smart AIs that can help them. That can help them navigate the planet, and they can start doing stuff and learning how to live on there, right? And then once you can verify that it's suitable for humans, and that your rockets are reusable, so you can make sure it's suitable for life and reusability. Reusability. Okay. So you need those two, and then I probably don't know what I'm talking about again. I'm just 19. Just as a little disclaimer. But reusable rockets, so you can keep going back and forth and transmitting humans. And then suitable for life, so you can have more humans going back on it, right? So you just keep sending rockets back and forth to the planet. And this should take like several years, potentially decades, because it just takes really long to get to Mars. So you need like a spaceship with like dozens of people, maybe hundreds, and that just is like risky, and you need to make sure it works. So we're assuming this is going to take a long time, right? AI setting up base, that might take like a year or two, depending on how quickly your AIs are, because it's not that hard to actually build houses. You can build houses and like land and bases unbelievably quickly if you do it right. Like construction buildings will go up in literally weeks or even like a couple of months. So this is like not a problem. Setting up base is not a problem. We just need AI to get there so it can actually build stuff for us. Terraforming, that part is self-explanatory. Just make sure you do it properly. We're going to trust our nuclear engineers for that, so can't really talk on that subject. But once you have these three, you pretty much have human life on Mars. And then you ask, well, Elliot, what about keeping these? What about like feeding these humans and like entertainment and all this stuff and like swimming pools? How are you going to make that work? Well, this is another problem, right? To make it suitable for life, you need to tackle a bunch of other things that I didn't cover yet. To make Mars suitable for life, you need energy. So setting up base. Mm-hmm. 5 years? Yeah. Well, again, I don't think you need Tesla Optimus robots. Like those could be the first entities that you send to Mars. But I don't think setting up bases is going to be very difficult, especially if you make the bases easy to set up, right? If you're just like farming materials on the planet and then building up everything from scratch, sure, that'll take like 5, maybe 10 years. That'll take forever. But if you have like these little boxable homes and you have like proper like thermal insulation in them so you don't get too cold or too warm from the outside climate, that's like pretty easy to set up. And then once you have energy, you're pretty much good from there, right? You just get your food and all that. You can have farms, right? You can obviously have farms on Mars. You can have them indoors. Um, yeah, maybe after a little while, we'd probably want to get a few million humans on Mars before we do a gigafactory. But yeah, so hopefully this makes sense. Like food, food is like totally taken care of. You pretty much just get a bunch of seeds. You get a bunch of dirt that you ship on board. Dirt's like probably the most scarce part because dirt is quite heavy. It's hard to ship that on rockets, because of how heavy it is, and you need a lot of it to farm, right? So perhaps there's a way where we could like react chemicals together and produce some sort of healthy dirt, right? So like stuff with fertilizer, You can't use this iron oxide sand. You can't use that because it just won't let plants grow. It has iron in it. Um, you're pretty much trying to grow plants in rust, and that doesn't work. So we could use something like a redox reaction to perhaps change these substances and then rearrange them in a certain way. But that's for the chemists to figure out. So there's like a bunch of different fields that have to be involved here. Probably seen this already. Yeah, you get water from the surface, you melt the ice, you get food by having seeds that you import from Earth, and then you have farms and you have like plant life grow on Mars. Your sand and your dirt comes from chemical reactions. Fertilizer, more chemical reactions, and then oxygen. Damn, I didn't think of that. I need to search this up. How much mobile orbital station? Yeah, that so someone from my YouTube chat is just said make a mobile orbital station. So having like something that orbits Mars, and like absolutely, you'd probably want something like that. But the point is when we humans like when we are landing, you're still going to need that time gap between getting from Earth to Mars. So you could sit on this little orbital spacecraft for a little bit, but you know it's still time intensive and you need a lot of planning for that type of stuff. What was I talking about before? Oxygen. How to get oxygen on Mars. Okay, so NASA has made something that makes oxygen on Mars. Oh, I should have thought of this. This is obvious. So plants, you're gonna see where this is going. Plants have a process called photosynthesis. Right? Photosynthesis. And so this reaction pretty much goes like this. You have CO2 plus H2O, and you get C6H12O6 plus oxygen. So notice this oxygen here. Mars's atmosphere is like 98, 99% carbon dioxide. And if you have plants, if you have farm stuff there, as long as you have your dirt and fertilizer and your water, right? You would get water from melting the surface, and you get your dirt and stuff from doing chemical reactions and importing it from Earth. You could have plants, and these plants would make oxygen for you. So there's that, and then you have to consider like this sand, this iron oxide sand that has 3 oxygens in it as well, right? So maybe you could like extract iron from it and then use the oxygens for breathing. And then use like iron from materials or whatever. I don't know how you would extract that efficiently though. That sounds like a difficult problem. But yeah, I don't know. That's like my super comprehensive plan. That's like super messy. That probably doesn't work. So yeah, that's that's how you get humans onto Mars, I guess. What do you guys think of that? How much time would it take for trees to grow? For the oxygen? Yeah, yeah. So like I said before, if you're having plants grow, then you would probably want to have them indoors, right? So you'd want to have all your plants indoors. You'd have your robots build these plants and get them to start growing. And then I don't know, maybe after like a year or something, you would have enough oxygen for humans to just essentially sustain themselves in this little base, right? Because the plants are just constantly releasing oxygen. You have a bunch of plants in this giant facility, and they're all just releasing oxygen from the carbon in the atmosphere. And so you can yeah, maybe a year. I'm not sure. But yeah, keep in mind life is always wanting to spread out, so it wouldn't be an impossible challenge. Like it would probably be relatively easy. You just have to put in the work to getting plants everywhere and letting them grow. Yeah, you could. And that's the point. Um, this guy in my chat's uh I want to say this correctly. Asahi, is that how you say it? If we could live long enough, we could see something like that. Yep. If we could live long enough. And that's another problem that I want to touch on, but I'm not smart enough for yet. It's immortality, or medical AI for medical, right? So whether that's attending to patients so that they don't fall off beds when they're in the hospital, that's a very common cause of death. Um, in, like you could have that use case as well as I don't know, just inventing like a lot of very cool drugs using machines because humans aren't fast enough at it. Mm, yeah, it's worth putting some thought into, but I'll chill out on that for now. I'm gonna see if I can get some more people in here, and then we'll dive into nuclear fusion a little bit. That stuff is like really cool. Going to talk about nuclear fusion in a few minutes. Join if join if it excites you. And then we change the YouTube title thing to getting or explaining nuclear fusion. So manage. Weren't you in here in the last little talk I did just today? Hmm. Did you have anything you wanted me to talk about? Just like put stuff in either YouTube comments or like unmute in the chat, and I'll try to respond. Is YouTube my passion, or am I doing it on the side? Yeah, so it's more of a side thing. Um, However, I think it is important to build communities that try to approach ground truth about everything, even though it's really hard. We still need to make efforts as small little groups out there, and the point of this is to not only to get people like networks and try to like build up some social infrastructure here, but also to just, vibe, have fun. We're like a lot of us here are going to be changing the world, whether that's in a major or minor way. And so, if we can all be in the same place, that'll only accelerate our potential. So, obviously, there's not going to be, there might not be that many decelerationnists watching like how to build language models from scratch, right? That was the video that got me popular, and it's just kind of a little hub for people who are into that stuff to chill. But yes, this is part-time. This is something I do on the side, to list, I guess, to listen. Yeah, the main post. What do you mean by that? Hmm. Yeah. So in that case, like what content would do you think people would want to see? Okay. So anything AI based, anything ML based? Yeah. So I'm also trying to think of like a new video to make, right? Because we need to make another video in the next like week or two. Um, I'm not sure. But yeah, tutorials. Hmm. Yeah. 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 Is that how you found me, or how did you come across my whole channel thing and this? Okay. Mm-hmm. Okay. So that's that's what we do then. We do tutorials about like tech and then building things from scratch. Okay. That down. Tutorials. So, and that's another thing that I should linger on is like you can actually make tutorials that are like 3 or 2 minutes long and pull in a ton of views from it, right? Because when people want to figure out a problem, chances are they're going to click on the video that's like the least amount of time. So if all the other videos are 5, 10 minutes and you make yours 2 minutes, then they click on it. Ooh. Is it possible to do soil analysis from satellite imagery? Yep. Oh, that's actually a good idea. Um, yeah, I guess sort of my assumption initially, and that's a really good point you make, Asahi, is yes, you do want to use techniques like satellite imagery and computer vision for like predicting this stuff. But at the same time, if you do not have any soil or you want to capitalize on the regions that do not have soil, you're going to need to build up from the topics I described. So, using like pretty much making your own soil or importing it from another planet, right? Even though that's inefficient, you know, you might still need to uh, use techniques like that. But if we can, we'd probably want to try to find soil whenever possible. And that's where that's where we'd probably set up base, right? It's already there for us. Is anyone else gonna come in this thing? Like, there's like 8 people that reacted. They're like, yes, yes, we'll join it, and then there was like 2 people that came to this chat, so a little funny. Yeah, the attention span. I'm trying to make this fun, but it you know I was gonna think like maybe we could play games with some of the community members, but no one's joining, so there's not really any games we can play, right? The point was to have like 8 or 10 people in here and we could all like do something fun and talk about things like nuclear fusion and like space exploration, but not the case. Hmm. Yeah. You want to learn nuclear fusion? I can do like a very quick lecture. You would appreciate it? Okay. Um, okay. So this right here is an atom, okay? Uh, this is an atom, specifically a hydrogen atom, and it has how much does a hydrogen atom have? It doesn't have like just a plus, like a single proton, right? Hydrogen atom has 1 proton. Um, a helium atom would have, since a helium atom is normal, it's like balanced, it's neutral, it would have 2 protons and 2 electrons. And you probably remember learning this in maybe physics or something, or maybe you haven't. But even if I just play with magnets, let me grab some. So I have 2 magnets, right? One is positive and one is negative, or the sides are positive and negative accordingly, right? When I put these together, they attract. This magnetic force is very strong, given the like just that field around them is very strong. So this is something we actually have to overcome in fusion. So when you have a hydrogen atom and a hydrogen atom, and you want to fuse them together, you literally have to push them so hard that it overcomes that little magnetic barrier around it. This magnetic barrier is extremely strong, so you need to push with a very high force or a high molecular kinetic energy, right? Kinetic energy is like how fast it's moving. How much energy does it have as it's like moving in a trajectory? And so the higher that number is, the more likely these are to fuse together because they are more likely to that repulsion barrier, that magnetic repulsion barrier is less likely to overcome that kinetic energy force because they have such high energy, right? It's hard for the magnetic force to counter that once they have such high energy. So once you fuse these together, they become a helium, right? And the 2 isotopes we're fusing, they're actually called deuterium and tritium. And this goes to, well, 17.6 mega electron volts. So an electron volt is like 1 electron volt. I don't know if I can say this. 1 electron volt, 1.602 times 10 to the negative 19 joules. Very small number. But when you have 17.6 million of these per collision of atoms, that is a very large amount of energy. And not only do you get this, but you also get, your helium atom as well. The hydrogen plus hydrogen is helium. You could look at your periodic table to like verify that. But the point is, you have two hydrogens. That's a terrible H. And you combine them, and you get a helium, and some extra energy left over. And this is what happens after you fuse these together, right? So they've overcome this electrostatic repulsion barrier, and this thing cannot resist, and they just clump together. Because once they get inside of this, when they're out here, this thing is pushing out, and then once they get inside, this nuclear force is going to pull inwards, because of the net charge inside of there. And it's not going to be neutral like in this one. They're going to be two different hydrogens, so they're going to they're going to pull each other together. So the reason why we get this crazy number here is, and this is like kind of weird, it's literally because E equals mc squared. So I can't explain this. I can't explain why this happens, but there's a little bit of mass that you lose when you convert this to a helium. So say this is like a 1, the 1. Normally you would get a 2, right? Combine these, you get a 2. But there's this little thing called the mass defect, which I don't fully understand yet. And the mass defect essentially, it says instead of this being 2, let it be like 1.8 or something, or 1.9. Okay? And this is your mass. M. We know what C is. C is speed of light, so you square that number, and you end up getting, like, C squared is 9 times 10 to the 16. You actually do the math. It's 9 times 10 to the 16. That's a very large number. So if you multiply your little mass, your little, 0.1 difference, because this 2 that you're supposed to get minus the actual mass that you got is your mass defect, and that's the mass that was converted to energy using this formula. So you multiply your 0.1 by 9 times 10 to the 16, and you get an absolutely ridiculous number, and that's your energy from fusion. So hopefully that makes sense. And then, yeah, I'll let you ask questions now, because that's a lot of material. You said, how precise is it? How accurate? Are you using Instagram or LinkedIn? This is YouTube, but I do not use Instagram, only LinkedIn. Can you define what you mean by how precise is it, or how accurate? I didn't see when you sent that message. But, so this whole thing of fusion gives you a bunch of energy, right? And so you ask, well, Elliot, how do you even get these to get so hot or so much kinetic energy that they smush together and fuse? How do you get them to have such a high amount of energy? Surely you'd have to heat them up to like millions of degrees Celsius. And that's true, you do. So there's actually 2 methods you can use to heat these up. One is a magnetic field. So you have like, what do you call it? You ever seen a donut before? This. There's this little thing in the middle. This is your magnet, M. And what you do is you put all of your deuterium and your tritium isotopes in there as gases. And then this magnetic field, since these have charges, they will be bound to act on a magnetic field that they're going to move. So the stronger the magnetic field, the more these are going to move, the higher the kinetic energy they're going to have. So you fill in the blanks, right? You make your magnetic field really strong. You make this really, really high. You put in a bunch of energy into it, and you heat these up. They collide, and you get your fusion output as heat, right? It's going to release a bunch of heat from that, and you in turn use that heat to boil water, which then turns into steam, and you have a turbine up here, and that spins, and it generates power. That's how fusion works. That's how fusion power plants work. But fusion is just this atomic reaction, essentially, that gives you your 17.6 mega electron volts. That's your actual fusion reaction. So this is version 2 right here, and the reason I say it's version 2 is because it's the more modern version. This is how nuclear fusion is done today. So yeah, you have this thing that's called a tokamak, and that's your little donut thing that spins around. The magnetic field, it's constantly making your hydrogens move faster and faster until they become so fast and full of energy that they just smash together, and you get your fusion. And then V1 refers to something called fission. Let me actually get a name up here. So fission is pretty cool, but it's not so good for the environment. Fission is like taking a uranium, or a U. You take your U, and this uranium is very likely to decay, right? It's going to decay into lower level, I guess, atoms. It's going to release energy as it decays into different atoms, and so you get some energy output from that as uranium decays. It's very unstable, so it's going to decay into things like EH or thorium, and then that's going to decay into EB, which is lead. That's your danger, right? Lead is not very good for the environment. If I don't know if you've ever seen what happens to people when they get lead poisoning, but their brain doesn't work, their heart doesn't work. A lot of things start to malfunction, or their offspring their offspring end up suffering from it. So lead poisoning is bad, and that's what fission gives you. Through each step of radioactive isotopes, or radioactive elements, sorry, because these are not isotopes, these are different elements. So uranium will give off some particles as energy, and then that will decay to thorium, and then thorium will decay to lead, etc. And through each phase, you get a little bit of energy released, and that energy is sort of used to spark other things from happening, other reactions in this little fission thing. So it's like an exponential reaction, and that's how you get your like fission bombs. So that's just your activation for starting this nuclear reactor, the fusion reactor, the one that fuses them together. Fission is when they're like breaking apart, and you have like some particle, like a neutron, break off of like an uranium atom, and it like breaks off. That'd be an example of fission, where you have things detaching, but fusion is like when they're combining and making something bigger. So you get some energy out of fission, and you use that to essentially activate the fission reaction, and that's how V1 activation energy works. So that's my little fusion lecture for you guys. And there's a bunch of papers on this stuff that you guys can look into, but that's all I'm confident to talk about right now. Anything else would likely be misinformation. You want to connect with me on LinkedIn? Yeah, so just search up. I can put a LinkedIn thing in the chat here if you guys want that. So here you go, my LinkedIn. Um, and then are you an AI developer or AI engineer? I'm a student. I'm 19. I'm neither of those. Also, you know what? Before I answer so quickly, can you define what an AI engineer is or an AI developer? What's the difference? So AI engineer solves problems using AI, and then developer just literally develop stuff, so build stuff from the ground up without an initial problem or a problem that's less urgent. Okay. Yeah. In that case, I'm probably an AI developer. I don't know, but only 19 and you know very much. Yeah, I get that a lot. But I don't know very much because, again, I'm just 19. I do not have life experience. So, th thank you for the compliment, though. I appreciate it. The fact that you're in the stream is good too, you know? But yeah, like, kid you not, a few years ago, I was not that smart. Like, I don't know. What? I guess you could say when ChatGPT came out, I was like absolutely mesmerized by it. I was like, whoa, this is crazy. You could learn so much with this. And then Andre Karpathy posted a video on how to build one. I was like, oh, this is cool. Let me try it. It was a little bit hard. I got through half the video and it was making sense. And then I was like, oh, Andre, you missed a lot of details here. I had to Google search a lot of stuff and like learn on my own. What the heck? It's like, Andre, I could build my own version of this and then just uh, put it on some famous YouTube channel like Free Code Camp, right? So it's like, oh, I've seen some tutorials there. They're pretty good. Expand your brand that way. So I reached out to Bao. He's the owner of the content manager there. And yeah, we did that. So I grinded for 6 months, learned everything I needed to know about the course. Spent a lot of nights looking out at the stars, staring up, being like, "Oh man, I'm not going to be there in my life, but hopefully someone else will." And that's your motivation, right? You're like, "Oh, if I teach, a few 100,000 people how to do this stuff, I get a little bit famous, and humans are smarter as a collective, so why not, right? Why not?" And you learn a thing or two by messing up. So there's like, you can never do anything perfect either. Um, I didn't give a perfect fusion lecture, but you guys could probably bear with me for most of it. Um, that seems to get humans pretty far. You don't have to get absolute perfection because then you just do not make progress. Instead, you try to do as much as you can with your materials, but don't over-engineer the crap out of everything. Just get stuff done. Build fast, fail fast, learn fast. You get the point. That's yeah, yeah, progressivism, right? I don't want to go as far as saying effective accelerationism, even though it's in my Twitter profile. But yeah. Plus, why the heck would you follow a movement when you could just derive everything from critical thought, right? You just use this thing up here. You don't need to trust those people on Twitter that just pretend like they're idiots. You're smarter than them. You can think about all the same things in your own head by observing the world and learning stuff that way, right? That's a skill on its own, is critical thought, which I wish humanity had more. But we'll do what we can. Who else is in the stream? One person watching. Um, you're still here. Okay. Hmm. Oh man, what do I teach next? So this is for. Oh, she is still in the stream. Well, that, bro. You're great. Is this stuff interesting to you? Just trying to talk about like fun subjects and all that. Are you the one in my YouTube chat? No? Okay. It's great actually. Okay. We can work with that. That's good. What next? Maybe we could do some coding. Oh, the output energy, like the ratio? Let's search that up. Yeah, I got this thing, unplugged it because I was playing a little bit of video games earlier and I needed the USB ports. But whenever I plug this in, just pop the USB cord in less than a minute, my GPT-4 Discord bot is running. So it's like super automated that way. Do I only use Python? Pretty much. I do some full stack development for a startup, but not that much anymore. So like full stack is like databases, SQL, Node.js, Node JavaScript for backend, and then React JavaScript for front end. But primarily, yes, just only Python for like the videos and stuff I teach. Plus, for anything like ML, deep learning, like any of that, you can stick with Python. You don't need to use anything else because everything is already implemented in C. Right? If you go to like PyTorch, it is implemented in Lua. Lua is a C-based language, right? It's effectively C. I'm not sure if how it compiles or anything, but it's apparently apparently the Meta team figured that out. So I trust Meta. It outperforms Google TensorFlow by quite a bit. So, you know, we stick with PyTorch for now. Until Mojo becomes better, then we might switch to that. But yeah, just only Python. That's my answer. Okay. Oh yeah, you asked a question earlier. It was about how much more energy does fusion produce as opposed to fission? Let's say per mole of the most efficient acid. Chain reaction. Yeah, per mole. That's what I was talking about. So uranium is U-235, which is a it uranium 235 is like refined uranium. So when you hear refined uranium, they're referring to uranium 235. And I'll explain to you how they make uranium 235 on a basic level. Yeah, so undergoes fission, splitting into two smaller nuclei along with a few neutrons and a considerable amount of energy. So it's like a bunch of neutrons bouncing. It's just a bunch of neutrons bouncing into other ones and making them react and stuff. So the energy released in the fission of a single U-235 nucleus is about 200 mega electron volts. Oh my gosh, that's a lot. However, to consider the energy released per mole, need a factor in Avogadro's number 6.02 times 10 to the 23 represents the number of atoms in a mole. So fission is approximately 1 order of magnitude higher. However, which one is more sustainable? Sustainable. And environmentally friendly. What startup that I work for? My dad's. Yeah. So you actually use a ton of energy just enriching uranium-238 to uranium-235. Accidents like Chernobyl and Fukushima have highlighted the potential risks associated with nuclear fission reactors, waste, greenhouse gas emissions. In terms of sustainability and environmental impact, nuclear fission has clear advantages over fission. It uses more abundant and less environmentally damaging fuel sources, produces less and less hazardous waste, poses fewer safety risks, and contributes minimally to greenhouse gas emissions. Yep. Shift to fusion as a primary energy source would present a significant advance in terms of environmental and safety considerations. Yep. So you have this. So consider this. These hydrogens that you have, that you can just do a simple reaction. You just like it costs almost no money to refine these. It's very easy to get hydrogen isotopes. They're very basic atoms, right? Well, you have something weird like uranium-235. I'll put it in green just because it's radioactive and people associate green with like toxic or radioactive. So I'll say U 238. You feed this into a mass spectrometer, right? And if you don't know what a mass spectrometer is, I'll explain. Mass spectrometers are very cool. So you have this path. It goes like this. And you have a magnet. And then say you have, we'll just put U-238 there. This 238 number represents the number of neutrons that it has. So it has the same number of electrons and protons or whatever. It just has a little bit more neutrons, okay? So 238 has 238 neutrons. So it's a little bit heavier, right? And if it's going into here, if it's going around this magnet, the magnet is going to pull it inwards. So it's going to take since it's a little bit heavier, it's more resistant to that pull by the magnet. So it's going to have a larger arc length, if you will. It's going to arc more. It's going to do this. And it's going to end up there. But if you put a 235 in this position, only has 235 neurons, so a little bit less heavy. And that'll take a slightly shorter arc length, like this. So notice 238 ends up here, and 235 ends up here. Well, if you just vaporize your uranium and you turn it to a gas, or you just put it into very small chunks, then you can effectively sort uranium-238 from 235. You just, you put a bunch of atoms in here. The 235s are going to have a shorter arc, so they're going to end up here. But all the 238s are going to have a larger arc, so they end up down here. So if you just have little bins, collect them, and then feed it away, you dump this out to a trash can or something, which is also bad for the environment. And then you keep these. Now you have your refined uranium-235. That's how you get uranium for fission. This stuff. So you take a bunch of clumped together 235, 238, and mixed up. A small percentage of it is going to be 235, and so you just separate them. You get all your 235 sorted in there, and your 238 sorted in there. And now you can do whatever you want with that. This little magnet just goes that. That's a mass spectrometer. YouTube. Just one watching. Okay. Yeah. Hopefully that makes sense. Yeah. I'm gonna clean this board off here. Yeah. I saw here. Are you still there? If so, you should join the call in my Discord server. I might end the stream here. Neon? Mm-hmm. Yeah, you're talking about if you use different, if you combine different atoms together instead of just two hydrogens. I didn't catch that part. It was hard to understand. Yeah, so that's another thing that a lot of people think. What if you combined different atoms to get more energy? Um, the reason that doesn't work, at least on Earth, is because you need a lot of energy to get them past each other. The bigger the atoms, the more that electrostatic barrier you have around it that is repelling stuff around it. So essentially, when you go up to neon, you're bumping it up like 10 difficulties, and you need like very, very hot substances that just you cannot produce on Earth sustainably. Uh, those are the types of things that occur in stars, right? So you could get all the way up to iron in stars until they go supernova. And it's just constant fusion. The hydrogen is like the least of their worries, right? Like hydrogen is pretty much fusing on the surface. Um, I'm not sure what our sun does. I think it does just helium fusion. Because at the center of the sun, it's only 23 million degrees Celsius, which sounds high, but compared to other stars and the temperatures you can get on like red giants is like absolutely nuts, right? You have that crazy gravitational force causing like a ton of friction and just it's like enormous. So yeah, and chances are if our sun can only do helium, then we probably don't only do helium here as well. We have produced higher temperatures than that though. We've produced temperatures up to like 5 trillion degrees Celsius in a particle accelerator, or rather a large hadron collider. So it's hadron is type of particle. I think sounds like a type particle, and you just smash them together, and then there's some energy released from the collision. So if you smash gold atoms together, the gold atoms are really really heavy. You can get temperatures up to 5 trillion degrees Celsius for like a very small blink of time. It's like very very minuscule, but you can hit temperatures like that. Yeah. You and the funny part is that you could literally put your finger right where that reaction is, and you wouldn't feel a thing, because it's like, you know, just a few atoms, right? So like a 5 trillion degree collision could be happening like everywhere all over your body. You probably wouldn't feel it. Um, yeah, I'm gonna end stream here.